Just a minute, I am starting recording. Yeah. So I will just revise the given data. So this length, effective length, this is simply supported span 5 meters, width 230 mm, overall depth 550 mm, AST is given as 1256 mm square, ASC 402.12 mm square, then clear cover is given as 40, sigma CBC for M20 grade of concrete from table 21, it's 7 MPa, and sigma ST for Fe415 from table number 22, IS 456, it's 230 MPa. So we have to find out here moment of resistance and the safe load carrying capacity of beam. So to start with, we will go for modular ratio, which is given by 280 upon 3 sigma CBC, again by IS 456 appendix B. That value comes out to be 13.33. Now to get MOR value, that is moment of resistance, very first thing we will have to calculate depth of neutral axis. Now to calculate depth of neutral axis, we will have to equate moment of area under compression to the moment of area of equivalent steel under tension about neutral axis. So first you can write down to calculate depth of neutral axis. So this will be the first step. And to calculate depth of neutral axis, what we have to do? We have to equate moment of area in compression with moment of area of equivalent steel, and where you have to take moment about neutral axis, right? So this is a very important step, this you should keep in mind. So if you are comfortable with this, then you need not to mug up the things, or you need not to go for rectification. You have to just remember that you have to equate moment of area in compression with moment of area of equivalent steel about neutral axis. This is to be done for what? To calculate depth of neutral axis. So for just sake of understanding, I will draw this cross section for you here. So at bottom there are 4 bars, that is tension zone, and at top there are 2 bars of 16 mm. The overall depth of section is 550, and overall depth is 550, 230 and 550. Width is 230, overall depth is 550. So this is AST, this is ASC.
Sir,
Yes, please.
so the equivalent area of area in tension एका स्टीलच आहे डायरेक्ट.
इक्विव्हॅलंट स्टील का ते सांगतो तुम्हाला आठवतंय यम घेतलेलं आहे आपण प्रत्येक ठिकाणी. आय विल ड्रॉ दिस स्ट्रेस डायग्राम फर्स्ट अँड विल लेट यू एक्सप्लेन दॅट.
ओके सर.
Now this is stress diagram. Here it is sigma CBC, and if you remember, we take it sigma ST upon M, right? Now why this M has come? Because this area in steel, now only steel takes the tensile stresses. As per assumption, concrete do not take part in tension resistance. So whatever area of टेन्शन झोन इज देअर, कॉन्क्रीटचा एरिया किती आहे टेन्शन मध्ये, हा एवढा आहे. बट वी आर नॉट कन्सिडरिंग दिस मच एरिया बिकॉज व्हॉट इज अज्युम्ड दॅट ओनली स्टील प्रोव्हाइडेड इन टेन्शन दॅट इज गोइंग टू रेजिस्ट टेन्साइल स्ट्रेसेस. Now if you consider this, instead of taking equivalent steel, you can make it equivalent area of steel, equivalent area of steel in tension. You can make this statement as well instead of going for equivalent steel. So why we are doing this? Because there is tension in bottom part or below the neutral axis, there is tension zone, and in tension zone there is concrete as well as steel. But as per assumption, this concrete is no more useful in resisting the tension. Only steel is going to resist that. That's why what is done, we are considering this equivalent area of steel. How we are going to consider? We are making it M into AST. Now what is M? It is the ratio of EC to ES. If you remember the initial discussion of modular ratio, so this is used to make equivalent area. That is the ratio, and that ratio, modular ratio, is used to convert this entire area into equivalent area. So that's why, as per assumption, we are neglecting concrete area and we are considering this equivalent area in tension. I hope it's clear.
Yes.
Fine. So this depth from top to bottom or to the level of steel, this is known as effective depth. So here the area in compression, area of concrete in compression is B into N, B multiplied by N. Now N is what? Depth of neutral axis from top fiber. This is N value. So N into B, this is the remaining. So whatever hash portion is now tension and remaining is in compression. So B into N multiplied by centroidal distance N by 2. So Bn square by 2 is the area in compression of concrete. Now along with concrete, in this case, there is compression steel provided as well in tension zone. Now this will be 1.5 m. So in case of compression, so we have to multiply modular ratio by 1.5. So this is also given in IS 456. So if you recollect that discussion, so this is the table number 22, wherein it is mentioned that we have to multiply modular ratio by 1.5. So from that, this 1.5 ASC, 1.5 times ASC, this is equivalent area of steel in compression. So this ASC multiplied by 1.5. Now the centroidal distance of this area. So at this level, it is provided, and this particular distance is how much? DC. So N minus DC is the centroidal distance for this particular bar. So 1.5 m ASC into N minus DC. Now Bn square by 2, this is area in compression of concrete. But if you see, there are two bars provided, and this entire Bn square by 2 is not the area in compression of concrete. So we have to neglect or deduct these two bars. So that's why minus ASC into again that N minus DC. So this is the area in compression, moment of area in compression, which is to be equated with moment of equivalent area in tension. So MAST. Now as this is in tension, that's why we are not multiplying M with 1.5. So M into AST, and its centroidal distance is. Now this is the centroidal distance. Now how much this will be? Total depth is D minus N. That will give you this centroidal distance. So D minus N. I hope this is clear to all of you. सगळ्यांना clear आहे? इथपर्यंत क्लिअर आहे सगळ्यांना? Okay. So at any step, if you are facing any doubt, feel free to ask me. Okay, fine. So here we will have to first calculate DC value and D value. So I will just zoom in for you. This figure will be bigger in that case. So here the clear cover is defined in the problem. Clear cover means below the face of this bar. या फेसच्या खाली किती दिलेलं आहे डिस्टन्स? दिस इज गिवन टू बी 40. सो वी हॅव टू find out effective depth and DC value. Now DC value is measured from where to where? It will be measured from the center of bar to the top edge. So from this to this distance is 40. So we have to add in that. So DC equal to clear cover, that is 40, plus half the bar diameter, plus half the bar diameter. So for compression zone, 16 mm bar diameter is used. 16 by 2 is 8. 40 plus 8 is 48 mm. So DC value is 48 mm. लक्षात आलं DC कसं कॅल्क्युलेट केलं? Yes, please, all of you, DC, whether it is clear to you?
Yes, sir.
Yes, sir.
Okay. Next, we have
Yes,
to
sir.
calculate D value. So now D is what? D is measured from the top to the center of bar. Now overall depth is 550 mm. So 550 minus, we will deduct clear cover. Clear cover is 40, and again from that you have to deduct half the bar diameter. Half the bar diameter. Now for tension steel, bar diameter is used as 20. So 20 divided by 2, it will be 10. So 500 mm is the effective depth. लक्षात आलं सगळ्यांना?
Yes, sir.
Okay, fine. So with this, we have calculated D as well as DC value. So that will be incorporated in this expression here. Right. So B value is 230. So if you convert it into meter, it will be 0.23. So all the values are in mm. You can continue with mm only. So 230 multiplied by n square divided by 2 plus 1.5. M value is 13.33. ASC value, I believe it's 402 into again n minus DC we have calculated as 48 minus ASC again 402 n to n minus DC 48 equal to M again 13.33 into AST, I think it's 1256 into D is 500 minus En. Now if you simplify this, you will get quadratic equation in terms of En. So if you simplify this term, entire expression, you will get quadratic equation in terms of En. So simplify on calculator and tell me the value of En. Yes, please let me know the value of En, what you are getting. Yes, anyone has done it?
189.32.
Right. So 189.32 mm is the value of N what you are getting. Now as we have done it in singly reinforced beam, similarly here we have to identify whether it is going to be over reinforced section or under reinforced section. So for that you will have to calculate critical neutral axis depth or depth of critical neutral axis. So depth of critical neutral axis you have to calculate. So which is equal to K into D. So K is the neutral axis factor and that can be calculated as M sigma CBC divided by M sigma CBC plus sigma ST and multiplied by D. So D is already known to you. So NC will be 13.33 into 7 divided by 13.33 into 7 plus sigma ST is 230 and D value is 500. So this comes out to be around 144.398. Just check this value, what you are getting.
145.
Okay, fine. So here we will be getting relation between N and NC. So NC value appears to be less than N. So N is greater than NC. So what type of cross section this will be, under reinforced or reinforced? Yes, please. Which type of section this is?
Over reinforced.
Yes, as this depth of neutral axis, actual depth of neutral axis is greater than critical neutral axis depth, this section appears to be over reinforced. So this is going to be over reinforced section. Right. So hope all of you are getting clear idea about this. As we are getting N to be greater than NC, the section is over reinforced. If N would have been less than NC, it would have been designed as or analyzed as under reinforced section. So here, so we'll first calculate sigma dash CBC value. Now sigma dash CBC is what? I will once again draw the cross section and stress distribution diagram. So 2 bars in compression zone, 4 bars in tension zone. So at the level of these bars, so whatever stress is developed, it is going to be sigma dash CBC. And the stress at top fiber, this is sigma CBC. So this value first you will have to calculate sigma dash CBC, then only we will be able to calculate moment of resistance. Now to calculate this, what we are supposed to do, we will consider similar triangles. Now this depth is N, so this is DC. So we can consider these two similar triangles in compression zone, and from that we can calculate sigma dash CBC. So this particular will N minus DC. So we will consider similar triangles in compression zone. So sigma CBC upon N equal to sigma dash CBC divided by N minus DC. So sigma CBC is 7, N value is 189 This is equal to exact n value. I will just 189.32. So 189.32 equal to this value. We have to find out sigma dash CBC. So AN is 189.32 minus DC value is 48. You just simplify this term and let me know the value of sigma dash CBC. Five point.
5.22.
Okay, fine. So 5.22 Newton per mm square. So this is the value of sigma dash CBC. Now we will go for calculation of moment of resistance. So moment of resistance offered by this doubly reinforced section. So equal to half sigma CBC B into N. So this is because of this is the force C1 multiplied by lever arm D minus N by 3 plus we will now consider C2, that is 1.5 M minus 1 ASC into sigma dash CBC into D minus DC. Yes, using this expression, you can find out the value of moment of resistance. Now, as we are getting over-reinforced section, we are considering compression force for calculating moment of resistance. So we are calculating this moment of resistance by considering compression force. So this one is because of concrete alone, that is C1. This is because of force C1 and this is because of force C2. Now C1 will be acting at centroidal distance of this compression zone and C2 force will be acting at the level of compression reinforcement C1 and C2. Yes, tell me the value of moment of resistance now. Half sigma CBC 7, B is 230, N is 189.32, D is 500 minus 189.32 by 3 plus 1.5 into 13.33 minus 1 into ASC is 402 into sigma dash CBC, it's 5.22 multiplied by D minus DC. D is 500 minus DC is 48. Simplify this, tell me the value of moment of resistance. Yes, please. What is the value?
90.75 into 10 raised to 6.
Okay. All of you getting same value?
Yes, sir.
Okay. 90.75 kilonewton meter. Right? So this is what moment of resistance is offered by this doubly reinforced section. Now we have to calculate the superimposed weight that can be resisted by this given section. Now for that we will have to first write down equation for external bending moment, and then we have to equate it with this moment of resistance. So you can write down equating external bending moment with moment of resistance. So now this was the simply supported beam subjected to UDL. So the maximum bending moment will be WUL square by 8, and this is equal to 90.75. So just find out WU value from this expression now. EL value is 5. So WU equal to 90.75 multiplied by 8 divided by EL square, that is 5 square. Now tell me the value of WU. Yes, what is the value of WU?
29.04.
29.0.
29.04. Yes. Now, what is asked in the numerical? You have to calculate superimposed load. Now, superimposed load means excluding self-weight. So, you have to keep in mind superimposed load means it will be totally external live load acting on the beam. So, to calculate that, whatever WU you have got, so from that you will have to exclude or deduct the self-weight of beam. So, first we will calculate now self-weight of beam, which has to be deducted. Self-weight of beam. So this will be equal to B into D into gamma. Gamma is nothing but unit weight of RCC. So width here is 0.23, overall depth is 0.55, multiplied by unit weight for RCC is 25 kilonewton per cubic meter. So tell me the value of self-weight.
3.1625.
3.1625 kilonewton per meter. So superimposed load. So this will be equal to this WU minus self-weight. So 29.04 minus 3.1625.
25.8775.
Make it 25.88 kilonewton per meter. Now this is the superimposed load which can be carried by beam. Now, if you still want to calculate working load, now this is the ultimate load can be which can be carried out. If you want to calculate working load, so you need to divide this 25.88 divided by 1.5. This is partial safety factor for load. So if you divide this ultimate load by this partial safety factor, you will be getting working load. What will be it is? What's the value?
17.25.
17.25 kilonewton per meter. So yes, so this is the working superimposed load that can be safely carried by the given beam. लक्षात आलंय सगळ्यांना?
Yes,
Yes,
sir.
sir.
Yes, so this is how this entire analysis of doubly reinforced beam is supposed to carried out. So with the given data, first thing you have to do is you have to calculate depth of neutral axis. So whatever data is given, you have to note it down. Then you are supposed to go for calculation of uh, depth of actual neutral axis. Before that, you can get the value of a modular ratio as 280 by 3 sigma CBC. Then to calculate neutral axis depth of actual neutral axis, you have to equate moment of area in compression with moment of equivalent area of steel in tension. So that expression comes out to be this Bn square by 2 plus 1.5 m ASC n minus dc minus this steel compression steel area, and its moment is to be deducted. That's why this minus ASC into n minus dc. Then it is equated with this equivalent area in steel and its moment about neutral axis. So MAST is the equivalent area, then D minus N is the that geometrical distance, CG distance from neutral axis. So simplifying that, you can get depth of actual neutral axis, then you have to calculate depth of critical neutral axis to identify whether the section is under reinforced or over reinforced. So NC, it is equal to KD, where K is the neutral axis depth parameter or design constant. So M sigma CBC upon M sigma CBC plus sigma ST. So that will be K value multiplied by D. So once you get NC value, you have to compare it with N value. And if N is more than or greater than NC, it's a over reinforced. And if N is less than NC, it will be under reinforced. If somehow you get N equal to NC, it will be a balanced section. So then you have to calculate sigma dash CBC value, that is stress surrounding the compression steel bars, stress in concrete surrounding or at the level of compression steel bars. So by using similar triangles from stress diagram in compression zone, so you will be getting sigma dash CBC value. Knowing that value, you can get value of moment of resistance. Then equating external moment with moment of resistance, you will be getting the ultimate load that can be carried, but it will be including self-weight. If you need to find out superimposed load, you have to exclude self-weight from that WU value. And if you want working load carrying capacity, divide the final value what you are getting by 1.5, which is partial safety factor for load. And the final answer, you will be getting working load carrying capacity of given beam. Is it clear to all of you?
Yes, sir.
Okay. So with this, we will finish with the working stress method. So we will move on to LSM, that is limit state method or limit state design philosophy. So initial part already we have covered in first semester, wherein we have studied LSM applied to structural steel design or design of steel structure. So in limit state method, in case of steel structure, what we have studied, so there were two limit states. One was for strength limit state of strength, and another was limit state of serviceability. Now, similarly, when we are applying this LSM to RCC, we have to deal with limit state of collapse and limit state of serviceability. Along with that, here one more thing, we have to go for limit state of durability, which deals with fire resistance and chemical action or accidental failure. Durability, check for durability or and this limit state of serviceability will be tackled in that way. So here, first we will be dealing with different limit state under collapse, serviceability, and durability. So once you clear with that, then we will go for stress strain behavior and what exactly there is difference between WSM and LSM approach, that we will see. So basically WSM, if you remember, we have used stress diagrams for the analysis. So just now we have solved one numerical. Therein also we have referred stress diagram as a base, but when we shift to LSM, we will be dealing with strain diagram. Stress and strain, that is the basic differentiation you will be coming across when we will start with the LSM. Should I continue with the LSM now? If you are comfortable, I will proceed further. Just let me know. Yes, please let me know. Should I continue with LSM or
Yes, sir.
later on you want to continue? Fine. Okay. So I will just take you to IS code now. So this section 5 is devoted for limit state method. So like previously we have seen that Annex B, which deals with working stress method. Now this is section 5 wherein the guidelines related to limit state method, those are given. So here all the limit states are defined here. Limit state of collapse, then limit state of serviceability, in that deflection, cracking, different things are given. Then next, characteristic design values and partial safety factor. So there may be questions based on characteristic strength, characteristic load. So already I have talked about this in initial discussions. So I will just remind you that there may be questions based on these two clauses, 36.1 and 36.2. Then design values, how to calculate that? So for that you will need partial safety factors. So what exactly partial safety factor means and why it is called as partial safety factor? So everything is mentioned in this under this clause number 36.4. So these are the values mentioned here. Table number 18, you can note it down in your notebook as well. Table number 18 will give you idea about different partial safety factors. No doubt these are more or less similar to the first semester wherein we have studied table number 4 from IS 800. Similar to that, this table number 18 is there with little bit modifications. So 1.5 you can see here, dead load plus imposed load combination whenever you are going to use. For dead load and imposed load means you can consider it as live load. So for that partial safety factor it's 1.5. right? And for limit state of serviceability, partial safety factor will be always 1, because we will be dealing with working load for checking serviceability. For strength, partial safety factor will be 1.5. Now these are the assumptions related to limit state design philosophy. We have seen assumptions for WSM similar to that. These are assumptions for Elsm. So plane sections normal to the axis remain plane after bending. This is classical bending theory or pure bending theory assumption. Same is applicable everywhere. Then B, second assumption, the maximum strain in concrete at the outermost compression fiber is taken as 0.0035 in bending. Now, as just now I told you that we will be dealing with strain diagram in case of ELSM. Now, if you see here, this is typical stress strain curve for concrete. Can you see this diagram? Diagram this case again, na?
Yes, sir.
Yeah. So whatever that thing is mentioned in second assumption, the maximum strain developed in outermost compression fiber is taken as 0.0035. So it is mentioned here. So related to 0.0035, the stress values developed, these are given here. So there are three values you can see. One is FCK, second one is 0.67 FCK, and third one is 0.67 FCK upon gamma m. Now gamma m is the partial safety factor for material. So this, the bottommost value is considered as design curve. So this particular curve, the bottommost curve, it is known as design curve. So 0.67 FCK upon gamma m, this value will be used as a stress value corresponding to maximum strain. So when maximum permissible strain reaches to 0.0035, corresponding to that stress value in concrete will be 0.67 FCK upon gamma m. So this diagram mostly we will be referring for most of the calculation. So this is the design value what you will be using. So moving to next assumption. So the relationship between the compressive stress distribution in concrete and strain in concrete may be assumed to be rectangular, trapezoidal, parabola, or any other shape, which results in prediction of strength in substantial agreement with the results of test. So it means that whatever shape is assumed, it will be combination of rectangle. So if you see, this is the stress distribution diagram. So this XU is the depth of neutral axis. Then 0.42 XU is the depth or the level at which resulting compression force will be acting. So resultant compression force as like C in case of WSM. So therein that value was half sigma CBCB into N. In this case, that resulting value is 0.36 FCK into XU. So this is the total compression force and this is the nature or shape of stress diagram. Now this is combination of rectangle and parabolic. So up to this level, that is up to 0.42 XU, this shape remains to be rectangular and thereafter it follows parabolic path. So the same thing is mentioned here. Now this value of partial safety factor, it is given here as 1.5. Then next, the tensile strength of concrete is ignored. That is, the entire tension is taken care by steel only or reinforcement only. This is same as in case of WSM. The stresses in reinforcement are derived from representative stress strain curve for type of steel used. So it is mentioned in next figure. So this 23A and this 23B. So A diagram is for cold work deformed bars, but usually that won't be used. So most of the time we will be referring to 23B. So steel bar with a defined yield point. So here also there are two curves you can see. One is Fy and another is Fy upon 1.15. So 1.15 is the partial safety factor for steel. So you might have observed the partial safety factor for material, that is M. For concrete, this is 1.5, and for steel this is 1.15. So this can be asked in examinations. Whatever be objective type examination or oral examination or any other examination, there can be question based on this partial safety factor value for concrete and steel. For concrete this is 1.5, for steel it is 1.15. Hope you will note it down in your notebook as well. Right, so this second curve will be used for design purpose. So as this value is design value because you have applied partial safety factor. So Fy upon gamma m, this comes out to be design value. So the value mentioned in this assumption, you have to take it from that curve. The maximum strain in tension reinforcement in the section at failure shall not be less than Fy upon 1.15 epsilon, ES, that is modulus of elasticity of steel, plus 0.002. So minimum this much strain will be developed in case of steel. So if I draw the strain diagram, so for concrete, this top portion will be in compression, and this gives you idea about strain in concrete. So maximum value of this strain is given as 0.0035, whereas for steel this value is given in IS code, and according to that this value should not be less than 0.002 plus Fy upon 1.15 ES. So this is the strain diagram for reinforced concrete section. So this strain diagram most of the time you will be using for analysis and design purpose hereafter, because practically you will be using LSM approach only. So wherever you are using LSM approach, this particular strain diagram is highly essential. So if you are likely to appear for any competitive exam subjective type, so therein this strain diagram is highly essential. Apart from that, even if you enter in the design field, so you should understand this strain diagram. Now these values you have derived from IS 456. Now these values are available readily in IS 456. In assumptions only it has been stated the strain in steel should not be less than this value, whereas maximum permissible strain in concrete is equal to 0.0035. So you can epsilon CS, and this is epsilon right. So this is related to assumptions done for LSM. So the stress block concept is there. So that stress block parameters you need to calculate, and what exactly that stress block is, I will discuss now. So whatever stress diagram you have to go for, so that stress block parameters need to be calculated before you enter into design. So unless and until you calculate stress block parameters, you won't be in a position to analyze or design any particular RC section. Like what we have done in case of WSM, we have calculated some design constant. Similarly, in this LSM approach also, we have to calculate design constant. But before reaching those design constants, first we will have to deal with this stress block parameters. Now, what exactly stress block I will switch over to board now. So when you are reached your ultimate value, let me know so that I can stop unnecessarily. If I continue and if you are not getting the things, it won't be useful. So when you are stressed to your limit, let me know so that I can stop. Anyone can just let me know that sir, we are stressed now and you should stop. So I will stop immediately. So I will just take you through the stress block parameters now. So let's say this is RC section having width B and depth, overall depth D. Let's say it's singly reinforced section, reinforced with AST. And to the center of these bars from extreme top fiber, this will be effective depth. And then I will draw the stress diagram. So this is epsilon Cu and this is epsilon S. And this is depth of neutral axis denoted by XU. So this is strain diagram. And now I will draw the stress diagram. I will first draw the things and then I will explain you simultaneously. Okay, fine. So I will just now first explain you and then I will take you to further analysis. Now this is stress diagram. आवाज येतोय सगळ्यांना?
Yes, sir.
Okay, fine. So this strain diagram and stress diagram. Now the distribution of compressive stress across the depth xu of concrete in compression. So this particular shape is known as stress block. Now this upper portion. Now this is known as a stress block. Now what it gives you? So this gives you distribution of compressive stress. This gives you idea about distribution of compressive stress in compression zone. Distribution of compressive stress in compression zone and up to which depth xu, because this compression zone is limited to neutral axis, up to neutral axis only. So this stress block is nothing but the block or the zone which gives you idea about distribution of compressive stress in compression zone, right? So this is known as stress block, and there may be question based on stress block or stress block parameters. Typically in IES exam also a few times there was question based on stress block parameters. Now the constants or the parameters which gives you clear idea about this stress block behavior or stress block shape, those particular parameters are known as stress block parameter. And if you see here, the constants are k1, k2 and k3. So these three constants k1, k2, k3, these are known as stress block parameters. So these are known as stress block parameters. Now if you just compare this with here 0.42 xu, this is stress block parameter, figure number 22, page number 69, you can note it down in your notebook as well. So if you compare this, here you will be getting value of two constants. So K2 into XU is the depth of force, and if you see here 0.36 FCK into XU, if you compare this value with this one, which is equal to K1 into FCK into XU. So here K1 value directly you are getting 0.36, right? And this depth is given by K2 into XU. So K2 value is equal to 0.42. K1 is 0.36, K2 is 0.42. Similarly, K3 also can be calculated, this particular distance. So I will not go into details of that, how to calculate that. So somehow if you appear for conventional theory exam, there may be question related to calculation of stress block parameters, maybe. Very rarely it may be asked. So all the things are available in reference books. I will not go in details how to calculate that. I will directly share the values of these stress block parameters. So K1 is 0.36, K2 is 0.42 and K3 is 0.45. So once you put all these values, you will be able to clearly draw this stress block diagram. So this value already we have seen, epsilon Cu is 0.0035 maximum value, and strain, this value should not be less than 0.002 plus Fy upon 1.15 ES. So this is how you have to arrive at this. Now there is change in this stress block shape at the level of 0.2 strain. I will just draw the compression part. This value is 0.0035 and somewhere here it will be 0.02. And for this stress block will be like this. The final shape of stress block will be like this. Just a minute. So this is 0.002 level. So up to 0.002, it will be rectangular in nature up to this point, and thereafter this variation appears to be parabolic. So this distance in stress block, this is K3, so which is equal to 0.45 FCK. Then the force at which resultant act, the distance, that is K2 distance you will be getting here. So K3 is 0.45. So this K3 comes here. K2 will come in picture here, and this depth is 0.42 XU. And the C value, the total force acting at that level, so that 0.36 FCK into EXU. So here K1 comes in picture. So this is the value or the shape of stress block, and below this it will be just straight line T. Similarly, for stress it won't be straight line for strain. So this is epsilon S, and here it is total stress value T equal to AST into Fy. Straight away you will be getting this. So this is all about stress block parameter which we will be using for further analysis. Now similar to WSM, there will be modes of failure in case of LSM as well. So that I will deal with first before going for analysis. So I will just discuss it from LSM point of view. Remaining things will be similar to WSM only. Modes of failure. So these are balanced, under reinforced, and over reinforced. Okay, so we have three strain diagrams now. This is first one, second and third one. So can you tell me which are these three different modes of failure? First one कुठला असेल, second कुठला असेल, third कुठला असेल? Tell me first mode of failure, second mode of failure and third mode of failure. Yes, please, can you hear me?
Yes, sir.
Yes, tell me all three types.
Balance, under and over.
Balance. First one is balanced, okay.
Second, under reinforce.
Second one is under reinforced and third one is
Over reinforce.
okay, fine. So this is balanced. This is under reinforced. And third one is over reinforced. If you see this, there is difference between LSM and WSM. So in WSM, what we have done, we have used stress diagrams we were using in case of WSM, and when you are dealing with LSM, you are using strain diagrams. So this is the basic difference between WSM and LSM. I hope you are getting this. So when we were talking about WSM modes of failure, there we have talked about so how the stresses are or the stress values at extreme fiber that we have considered. But when we are now discussing about modes of failure as per or with regards to LSM, here we are drawn strain diagrams. Now, if you see the first section wherein steel and concrete, those are reaching their maximum permissible values simultaneously, epsilon Cu and epsilon Sy. Now, in case of under reinforced section, what is happening? The steel has reached its maximum value, but concrete has not reached its maximum permissible strength. So if you see epsilon C is less than epsilon Cu, when the steel has reached its maximum permissible value. So in this particular case, the failure will be ductile. So in this case, ductile failure you can observe, and whatever failure will be there, it will be primarily because of tension failure of steel. Now in this case, you can see the actual neutral axis has shifted upward compared to balance section neutral axis or critical neutral axis. So XU max is the balance section depth of neutral axis. So compared to that, XU has moved upwards in case of under reinforced section, whereas in case of over reinforced section, if you see that neutral axis has moved downward and XU is more than XU max. So if you see in this, the concrete has reached its maximum value, whereas steel is still unstressed, or the strain in steel is much lesser than the maximum permissible value. So in that case, so this will be brittle failure, because concrete is going to fail first prior to steel reaches its value. So in this case, this will be brittle failure, and such failure won't be expected by any designer. So this is about modes of failure. So there may be question related to comparing. In case of your oral examination, you may have to compare modes of failure based on WSM and ELSM philosophy. So therein you have to draw these sketches separately for LSM and WSM. LSM will talk about strain distribution, whereas WSM will talk about stress distribution. The remaining things are altogether same, means percentage of steel or quantity of steel used with respect to balance section. So that you can elaborate primary mode of failure, primary ductile failure, then brittle failure, tension failure of steel, compression failure of concrete. So all those points remain same. The basic difference is stress distribution and strain distribution. लक्षात आलं सगळ्यांना? Okay, is it fine?
Yes, sir.
Okay, continue करू पुढे. Yes, please tell me, should I continue?
सर उद्या घेऊ ना.
ओके फाईन, दॅट्स व्हॉट आय वॉज एक्सपेक्टिंग. मी इथेच विचारत होतो, तुम्हाला कळत असेल तर घेऊ किंवा उद्या कंटिन्यू. फाईन. सो आजच्या इथपर्यंत कोणाला डाऊट आहेत काही?
हो सर.
हो सर.
ओके फाईन.